Let f of x be an everywhere differentiable function. An example is shown in blue. A straight line is shown in black. We can calculate the slope of the straight line. We use this to introduce the definition of derivative. By taking the limit as x goes to 3, we find f prime of 3. And then more generally, we'll consider f prime of a. But then for some reason, we don't want to express the derivative as a function of a, so we rewrite it in terms of x. And in fact, we change the definition of derivative so that the change in x is denoted by h. This seems to be the preferred definition of derivative because it emphasizes the fact that it's a function of x. Now the same picture occurs again when we introduce the mean value theorem. And this time we don't typically let h denote the change in x, but I would like to. So for this talk, h denotes the change in x. Just like with the definition of derivative, this is a trick for switching from a specific point like x equals 3 or x equals a to a general x. The fact that w is somewhere between our two x coordinates can now be expressed by saying that delta is bounded. In fact, it's between 0 and 1. So the existence of such delta is the main conclusion of the mean value theorem. Let g of x be the straight line shown in blue. Let f of a be the area of the shaded region. We'll insist that x and therefore a are at least 0 so that g and f are positively valued. And we'll skip subtraction of areas in this discussion of integration. We know f of a well since we know the area of a triangle. Therefore we also know f prime of a equals ga. But I would like to understand directly why f prime of a is the height ga. So think of a as that value of x where you stop. The idea is that a slight increase in the stopping point results in a slight increase in the total area. So the bigger the height at the stopping point, that is to say the bigger g of a is, the greater the increase in area if you increase that stopping point just a little bit. Now let's replace a's with x's for the usual reason that we prefer to have functions of x. So now think of x as the stopping point. We want to know directly why f prime of x is equal to g of x. In fact, the change in f is an area, and it's equal to the area of some rectangle of width h, and height somewhere between g of x and g of x plus h. Divide through by h to focus on that height, g of x plus delta 1h. Convince yourself that delta 1 is between 0 and 1. Now we've also seen this ratio with the mean value theorem. Delta 2 is also bounded, also between 0 and 1. So taking limits as h goes to 0, we do see that f prime of x is equal to g of x. And that is what the fundamental theorem of calculus part 1 looks like on this example. So for a quick review of the fundamental theorem of calculus part 1, f of a is the shaded area. F prime of a is the height right there. That's the key point. Write the derivative of f in a different way. And finally, change the name of the endpoint from a to x. There's the fundamental theorem of calculus part 1. Okay, here's a really nice related rates problem. Sand is pouring from a pipe at a constant rate. How fast is the altitude changing at a particular altitude? Now for this problem, the important thing is that the cone is getting bigger. And if we want to, we may as well imagine the cone is turned on its side and the sand is being directly added to the expanding circular base. A really good reason for doing this is because we'll end up with a picture very similar to the picture that we've just been using. And I'm going to go ahead and change a for altitude into x again. So now f of x is going to represent the volume of the cone, and g of x is going to be the area of the circular base. You see how intuitively the change in f is going to correspond to the area of that circle. Although this time the change in f is actually a volume, it's also the volume of some cylinder of height h. Convince yourself that delta 1 should be between 0 and 1. It's bounded that way by the intermediate value theorem. In any case, divide through by h. Delta 2 is bounded by the mean value theorem, so take the limit as h goes to 0. We get that the derivative of f is the area of the circle, which we know very well. We can get the formula for the volume of a cone from here if we want, but let's go back to the original problem. With our new notation using x for the altitude, we found that dv dx is the area of that circle. Now multiply through by dx dt. The left-hand side is the constant given in the original question, and you're on your way. I personally really like how dv dx plays a prominent direct role in this solution. It's almost swept under the carpet with the standard solution, which, by the way, assumes the formula for the volume of the cone in the first place. Now we know how many r by r squares occupy the same area as a circle of radius r. We know the answer doesn't depend on r. It's a little bit more than 3. It's a little less than 3.5. In fact, it's pi. The definition of pi is usually based on perimeter. And now you should see the connection. But that's not actually what I wanted this for. This is actually going to be an expanding sphere, like a balloon. So the problem is that if a sphere expands at a constant rate, find dr dt for a particular value of r. This problem is quite a bit trickier than the previous one with the cone. But let's examine some similarities anyway. Now imagine drawing the solid red line. F of x will denote the volume that we get by revolving what we have so far about the x-axis. As usual, the derivative f prime of x is going to correspond to the area of an appropriate circle, and so we can use this to find the formula for the volume of a sphere. Remembering, of course, that f of 0 would have to be 0, so the most obvious antiderivative for f prime doesn't quite work. The blue line is in there for comparison because we just answered the question with the blue lines. We would get a cone if we revolved that about the x-axis. And if we do so, then the formula we just found shows that the resulting cone actually has half the volume of the half sphere. It's an interesting comparison. And so now we finished the problem in the usual way using the chain rule. So this isn't really different from the standard solution, except that perhaps we pause to consider dv dr, where we find a formula for the surface area of a sphere.